All right, let's look at the questions that I assigned from section 1.4. So this first question here, basically given a differential equation and an initial value, we're going to run through a few iterations of Euler's method. So part A, write the Euler's method iteration for this equation, identifying the values T naught and Y naught. Okay, so what are T naught and Y naught? So T naught is given as 0. Y naught is given as 1. And basically, I'm writing out this linearization of, so y sub k plus 1 is going to be equal to y sub k plus h. And what is my differential equation? That is going to be y cubed. So this is going to be generally what I'm going to do to follow for this question. So this is part A, basically just a kind of a rough setup. Then for part B, I'm going to approximate the first few values here. So let's set up a table. So I'm going to find y1, y2, and y3. So basically, I'm going to run through 3 iterations of Euler's method. So for the value k, basically we're starting with k0. I'm going to go k's 1, 2, and 3. And I'm going to find t. I'm going to find y. I know when k is equal to 0, basically, I know I'm starting at t equals 0, y equals 1. So what happens when k equals 1? So what do I do from there? Well, actually, before I get there, what am I doing with, these values of t and y? So I know that dy dt is equal to y cubed. So in this case, that will be equal to 1. So maybe I'll make another row in my table for now. So dy dt, make it really clear, this is basically going to be the previous column cubed. This will be 1. So what does that mean here? That means that, let's just keep adding columns. So what is h times y cubed? So for what I want to do, h is going to be a constant 0.1 y cubed. So 0.1 times 1 is going to be 0.1. All right, so this 0.1, essentially what happens with the 0.1, this is like my change in y. So my next y value is going to be 1.1. My next value of t, that is dictated by whatever my step size is. So I can essentially fill all those in now. This step is going to come at 0.1. Next step is going to come at 0.2, then 0.3. So now we begin the cycle anew. So what is, if y is equal to 1.1, then what is dy dt? Well, that's equal to whatever 1.1 cubed is, which I don't know off the top of my head. So 1.1 raised to the third power is 1.331. So that's my change in y as t changes. So for any small change in t, y will change by 1.331 times whatever that change in t is. And I know that change in t is going to be 0.1. So I'm going to multiply 0.1 times that. So that gives me 0.1331. And again, this rightmost column, this is essentially my change in y, which means I'm going to add this. So times add this to my previous value of y. So this becomes 1.2331. All right, so this is my new value of y at t equals 0.2. So I need to recalculate my rate of change. So I'm going to cube this value, 1.2331 to the third power. Now I'm going to have to start rounding. So now I have 1.87497, 87497. And we take a tenth of that because, so this is the rate of change of y with respect to t. If t changes by 0.1 units, then y will change by 0.187497 units. And I will add that to my previous value of y. And that gives me 1.4206. And that is actually as far as I wanted to go. So I don't want to go any further than this. Like when I say I don't want to go any further, I don't want to get any further y values. So I don't actually need to recalculate dy dt. So here are my approximations. Basically my y1, y2, and y3, that comes from these values here. 1.1, 1.2331, and 1.4206. All right. So that's B. Part C, solve the problem analytically if possible. So I should be able to do that. So part C, dy dt is equal to y cubed. I can separate this. So if I divide both sides by y cubed, I get dy over y cubed. dt equals 1. Multiply through by dt, I get dy over y cubed equals dt. So this has been separated so I can integrate. Okay. So from here, what is the integral of y cubed? Maybe it would help if I did this, or not y cubed, 1 over y cubed. This is the same as y to the negative 3 dy equals dt. So this becomes y to the negative 2 over negative 2. Y to the negative 2 over negative 2 equals t plus c. Or negative 1 over 2y squared equals t plus c. I'm going to go ahead and stop here and evaluate c because I have the means to do so. I know that when t is equal to 0, y was equal to 1. So that gives me negative 1 over 2 times 1 equals 0 plus c. So I get c equals negative 1/2. So negative 1 over 2y squared equals t plus 1/2. All right, so isolating y is going to be a little bit tricky here. So let's do this. If I can make both sides look like a fraction, I should be able to cross multiply. So on the right-hand side, I'm going to find a common denominator. So I get negative 1 over 2y squared equals 2t plus 1 over 2. Actually, I'm not going to cross multiply. I'm going to do this. I have a fraction equals a fraction, which means their reciprocals equal to each other. So negative 2y squared equals 2 over 2t plus 1. I'm going to divide both sides by negative 2. That gives me y squared equals negative, -1 over 2t plus 1. So finally, y equals, for now, I'll say plus or minus the square root of -1 over 2t plus 1. But I bet you my initial condition doesn't work with part of that. So if I plug in 0 for t, oh, something went wrong. This is not going to work. If I plug in 0 for t, then I get the square root of -1. Okay, so why'd that happen? Okay, let's go back. So did I separate this correctly? dy dt equals y cubed. So dy over y cubed equals dt. Y to the -3 dy. Y to the -2 over -2. Y to the -2 is the same as 1 over y squared. Should be negative. So when I said c equals -1/2, and then I lied about it in the very next step. Okay, so t minus a half. So -1 over 2y squared equals 2t minus 1 over 2, which this makes this a minus sign, and this a minus sign, which means this is going to be -1 over 2t minus 1 is equivalent to 1 over 1 minus 2t. If I plug in a 0 for t there, then I get plus or minus radical 1. But I don't want the negative sign of that. I just want the positive side of that. So this is what I have. Y of t is equal to this. So this is my analytic solution. Okay, so this is my analytic solution. So now let's do this. For this analytic solution, let's find values of y of 0.1, y of 0.2, and y of 0.3. All right, so y of 0.1. 1 minus 0.2 is 0.8. 1 divided by 0.8 is 1.25. Square root of that is 1.11803. 1.11803. Right, next. All right, so what about when t is equal to 0.2? So it'll be 1 minus, in the denominator, 1 minus 0.4. So 1 over 0.6. Square root of that. So I get 1.29099, and then finally 0.3. So 1 over 0.4, square root of that, and I get 1.58114. Right. So what are my errors there? So basically, so capital YI, those are my approximations. Lowercase yi, those are my exact solutions that come from my, my analytic solution. So 1.1 minus 1.11803, negative 0.01803, 1.2331, minus 1.29099. So they get more significant as you go. And this is a predictable problem with Euler's method, is that, whatever errors you have, they're typically going to start small, but they're going to compound. So finally, what's my error? 1.4206 minus 1.58114. So these are my errors from part D. So that is all from question 3. Let's go ahead and move on to our next question. All right, so I have this differential equation. So part A is to find the exact solution. So this is something I can do because the variables separate here. So part A, I can separate the variables into dy over 3y minus 1 equals dt. Integrate. The left-hand side is going to become a natural log, but I got to take a little bit of care because it's not going to be an exact multiple. So I'll do this. I'm going to multiply the inside of the integral by 3 and the outside of the integral by 1/3. So basically what I have here is 1/3 times the natural log of the absolute value of 3y minus 1, and that equals t plus c. I'm going to move the 1/3 up. So natural log of the absolute value of 3y minus 1 to the 1/3 equals t plus c. Now that I've moved that 1/3 up, I can exponentiate both sides. So now I get 3y minus 1 to the 1/3 equals essentially c to the t. I'm going to go ahead and stop here so I can evaluate c. So what happens when I plug in 0 for t? I get 2 for y. So basically 5 to the 1/3 equals c times e to the 0. So my c is the cube root of 5, essentially. All right, so let's keep going. 3y minus 1 to the 1/3 equals 5 to the 1/3 times e to the t. Okay, now I'm going to cube both sides. That gives me 3y minus 1 equals 5e to the 3t. Add 1 to both sides, 3y equals 5e to the 3t plus 1, and y equals 5e to the 3t plus 1 all over 3. So this is the exact solution. B, use Euler's method with step size h equals 0.5 to approximate the solution to the initial value problem on the interval 0, 2. Okay, so essentially we're going to do something similar to what we just did to approximate what we just did. So I know that I'm going to have t values. Let me mimic the table I just made. Okay, so we'll do k, we'll do t. Y, dy dt, and then h, dy dt. So starting with 0, how many steps do I need? I'm going to take 1, 2, 3, 4. So initially I have a t value of 0, y value of 2. What's my initial value of dy dt? 3 times y is 6 minus 1, which is 5. What is h times 5? So h is 0.5. So half of 5 is going to be 2.5. So again, that h times dy dt, that basically gives us our change in y. So 2.5 plus 2 is 4.5. Our t values, I can kind of fill in the t value or the t column in this table all at once. So 0.5, 1, 1.5, and then 2. So I got my first y value. Now we got to approximate. 4.5. So 3 times 4.5 is 13.5 minus 1, which is 12.5. Let me make sure about that. 4.5 times 3, yeah, 13.5 minus 1, 12.5. And then my step size is a half, so I'll divide that by 2, and I get 6.25. That's my change in y, so I add that to y, and I get 10.75. All right, so that new change in, or that new y will help me find my new dy dt. So 10.75 times 3 minus 1 is 31.25. 31.25, and then half of that is my change in y. So 15.625, and then I add that to my previous y, plus 10.75, and I get 26.375. And one last time through, multiply that by 3, minus 1, that gives me a dy dt of 78.125. If I divide that by 2, that gives me 39.0625. That's my change in y. So I'm going to add that to my y, my previous y. So 26.375, that's 65.4375. Okay. Says make sure my approximations are accurate 4 decimal places. I mean, only one of them really needed that. So sketch the graph of the approximate and exact solution. So let's do this. Let's go to Desmos. Yeah, I want to keep them. And let's try to put these side by side. Okay, so let's do this first. I am going to graph a bunch of points. 0 to 0.5, 4.5, 1, 10.75. So first I'm going to graph all the values that came from my Euler's method. 1.5, 26.375. And finally, 2, 65.4375. So those points, and then on top of that, I will also graph y equals 5e to the 3x plus 1 all over 3. All right, and if I did everything correctly, then these should be somewhat close to each other. And I'll probably have to zoom out to make sure. So I believe that my Euler's method approximation was reasonably good. So yeah, so I know that, I mean, we started from that initial point. Should I ask you to bear with me while I do this? Let's do this. Did I say the first slope was? Actually, I was going to put line segments between all the dots, but that I don't know if that how necessary that is. Well, did the question ask me to do that? Sketch the graph of the approximate and exact solutions. Yeah, let's go ahead and do that. So before that, let me look at the slopes. So let me graph 4 different line segments here. So I'll do them all in point slope form. So y minus 4.5 equals 12.5 times x minus 0.5. And I want to graph that from where to where? 0.5 less than or equal to x less than or equal to 1. Skip one. Y equals 5x plus 2. 0 less than or equal to x less than or equal to 0.5. All right, the third one, y minus 10.75 equals, what's that slope? 31.25 times x minus 1. And that goes from 0.5 less than or equal to x less than or equal to 1. And then the next one, y minus 26.375 equals 78.125 times x minus 1.5. And that goes from less than or equal to x, less than or equal to x, or to 1.5. All right, is that actually what I wanted to do? Let me see. No, not at all. So what did I mess up? All right, so this one did what I wanted to do. The blue did what I wanted to do. Oh. Please come back. All right, thank you. All right, that's better. Okay, so if we look at the line segments that I just put in here, this is essentially what Euler's method does. Is it takes your curve and it approximates it into a bunch of, let's do this as well. Let's only graph this thing where I actually care about it. So 0 less than or equal to x less than or equal to 2. So the red curve is the exact. No, to 1, sorry. The red curve is the exact. And the line segments, like all the other different colors, those are what Euler's method told us. All right, so yeah, thanks for bearing with me on that approximation, but I thought it was valuable to show you kind of what we were juxtaposing there. Was that everything that the problem asked us to do? Sketch the graph of the approximate and exact solutions. All right, good. So that was all the solutions for the questions from 1-4.